What you are witnessing is real footage of a coronal mass ejection, or CME. These extreme solar weather events occur as a result of electromagnetic activity within the sun. This electromagnetic activity causes a huge amount of energy to be released in what's known as a solar flare, in addition to billions of tons of coronal matter being ejected from the sun's surface. CMEs are extremely fast, traveling at speeds of up to 3,000 kilometers per second, and the accompanying solar flare can produce energies on the order of 10 to the 25 joules. These events are driven by a process called magnetic reconnection, and it's when the sun's magnetic field lines rearrange themselves into new configurations. For all intents and purposes, the sun can be thought of as a giant magnetic dipole, with magnetic field lines stretching from the North Pole to the South Pole. This is because the sun is basically a giant ball of plasma, charged particles like electrons and positive ions. The motion of these charged particles is what generates the sun's magnetic field. Because the sun rotates at a constant speed, particles near the equator have to move faster than particles near the poles in order to keep up, an effect known as the Coriolis force. Now, an ideal plasma will exhibit behavior consistent with something called the frozen-in condition. As particles in the plasma move, the magnetic field lines will move with them. The field lines are literally frozen into the fluid. However, these lines eventually reach a point where they're so stretched out that they're no longer in the most energetically preferred configuration. They have to rearrange themselves, and as a result, they end up violating the frozen-in condition. Instead of running parallel to each other, they reconnect to form loops, releasing huge amounts of energy in the process. So what's the deal here? How does magnetic reconnection produce the huge amounts of energy we see during solar flares and coronal mass ejections? What's the actual physics going on here? Well, the answer is we don't really know. Now, I know what you're thinking. What do you mean we don't know? We've made such a big deal about reconnection and we still don't know how it works? Is this all just a hoax made up by big science in order to sell you more science, like climate change or the moon? Not really. We mostly understand how reconnection works, certainly more than we did 20 years ago, but a lot of the physics behind it is still a mystery, one that physicists today are actively investigating. So buckle up, because I'm about to take you on a journey through the world of magnetic reconnection, from the very first theories to what we know now, successes, challenges, blood, sweat, tears, and how observation and experiment have contributed to our understanding of how it works. We begin with the Sweet Parker model from all the way back in 1957. Okay, welcome to Rowan's Derivation Corner. So, like I said, the sun is a giant ball of plasma, and these are the magnetic field lines as it rotates. So if we zoom in here, here's what we have. We have these magnetic field lines, which are coming close to each other, and we have plasma entering in at some velocity u in, and plasma exiting at some velocity u out. And so in here, where the lines are reconnecting, we have what's called the dissipation region. And so we can call this length L, and then call this width delta. So you might be thinking, okay, plasma is just charged particles. We're gonna be talking about, currents and things, so why not use Ohm's law? What is Ohm's law? V equals IR. Wrong. Maybe if you're a juvenile. What we need is generalized Ohm's law. So that is So this is generalized Ohm's law, and this is what plasma physicists use, and it's what we're going to use to solve this situation right here. So it may look complicated, but it's really just Newton's second law, right? This is the electromagnetic force. You might recognize it as the Lorentz force. This is force due to pressure gradients. This is the change in momentum. And then this is the drag force, so some force that is proportional to velocity. So even though the sun is plasma and it's made up of all these different particles, they kind of move together like a fluid, right? And so that's exactly the thinking behind magnetohydrodynamics, or MHD. So basically the idea behind magnetohydrodynamics is that we're treating plasma like a fluid, but the forces at play here are really electromagnetic forces. So let's look back at this generalized Ohm's law. It looks very complicated, but we can actually cancel some of these terms out. We can cancel this one out. because there's no magnetic or electric fields. And you might be thinking, what do you mean? There's magnetic fields right here. Well, the magnetic fields actually don't do any work on the plasma. You can think of the magnetic field as being almost part of the plasma here. So what I mean when I say there's no electric or magnetic fields is that there's no external fields acting on our plasma. We can get rid of this term because what we're going to be looking at is this system in a steady state or equilibrium, which is basically just saying, sum of the forces equals 0, because this is just Newton's second law. So what we're left with is just this drag term and this pressure gradient term. So the drag term is what we're using to model classical resistivity, right? So as these particles, move through, they're going to hit other particles on their way. So there's going to be some resistivity there, and that can be modeled by a drag force, which is proportional to their velocity. And this is the force due to pressure gradients. So as the plasma is being compressed, we can imagine that there's some pressure there. We don't know what exactly is causing this pressure, but that's okay. And you might be worried about this freaky double-headed arrow here. That just means that pressure is a tensor. What is a tensor? Well, it's complicated. And we're going to make another simplification here, which is that we're only going to consider the x direction. So we're only going to consider the velocity going this way and that way, and we're only going to consider pressure going this way and that way. So we're only going to consider pressure that's squeezing this plasma out. Okay, so let's start with this term here. So gradient U, what is that? Well, that's just the d dx u of x hat plus d dy u of y hat plus d dz u of z hat. Okay, but we only have velocity in the x direction, so we can just get rid of these other terms entirely. So gradient u is d dx u of x, and then u dot gradient of u. Well, again, our velocity only has a component in the x direction, so we're just multiplying this x component by the x component of our gradient here. So what you end up getting is u of x times d dx of u of x. So let's look at this term over here. This is the divergence of our pressure tensor. Now this is a tensor, so defining the divergence of this is a little more complicated, but just imagine for a second that this is just a regular vector, and we only have an x component here. So the divergence dpx dx. And I've dropped the little e subscript here. That just means the electron pressure, because we're talking about electrons here. Great, let's put it all together. Du x dx equals negative, don't forget the negative, dpx dx. Great. Okay guys, I made a mistake. I forgot to put this e here. So this constant should be 1 over e times ne. So let's write out our full equation. dx. And remember, we still have to multiply this term by this constant out front. And speaking of, I haven't really talked about the constants yet, so let's go over them right now. This is the mass of an electron, this is the charge of an electron, and this is the number of electrons. Why it's these constants specifically, don't worry about it, just know that it's what we need to make the units cancel out. Okay, so let's simplify further. We're going to multiply by E times Ne, and this quantity is referred to as the charge density. Okay, great. So these terms are going to cancel. And this, well, we have E, N, E, M, E, over E, so the E's cancel, and what we're left with is NE, ME. And this is actually the mass density, or the density as we would normally think of it. I know what you're thinking, it's not really a density because we have the number of electrons in our system times the mass of one electron, so really it's kind of the total mass, but don't worry about it, we're just gonna call this the mass density. Okay, so we have rho m times ux dux dx equals negative dpx over dx. Yay. Okay, so this is what we ended up getting for our force balance equation. Now, we want to find the change in pressure, because if we can find the change in pressure, then we can find the velocity. So what does this term really mean? This is the change in pressure as you move in the x direction. So, I mean, it's negative, but we're gonna have some dp dx, some change in pressure going this way. So let's define this dp as our change in pressure from x equals 0 to x equals L over 2. This is x equals 0. This is x equals L over 2. Now, ideally, we would want to find this delta P from x equals 0 to infinity, but because the pressure changes so much from 0 to L over 2, we can just treat L over 2 as being basically infinity. So we're gonna have some pressure here at x equals 0, and then some pressure here at L over 2, and then this delta P is our change in pressure from 0 to L over 2. Okay, so let's integrate this. We can do that, right? We can do whatever we want. Okay, so we're integrating from x equals 0 to x equals L over 2. I almost forgot the dx. Never forget the dx. Okay, so on this side, we're integrating dp dx with respect to x from 0 to L over 2. And if you remember from the fundamental theorem of calculus, this just turns out to be the change in p from 0 to L over 2, which we already said was delta p. So on this side, we get negative delta p. Okay, what about this side? Mathematicians are going to hate me for this one, but you can kind of imagine these dx's as canceling. So what we really have is u of x integrated with respect to d of x. Be careful, don't change your bounds. We're still going from x equals 0 to x equals L over 2. So we do this integral, we get ux squared over 2 from x equals 0 to x equals L over 2 is negative delta p. All right, so what is this? Well, to make things easier on ourselves, let's say that the velocity at x equals 0 is just 0, right? We can do that. We can define, our axes any way we want to. And then let's say u at L over 2 is u out. So that's this velocity here that we're trying to calculate. Okay, so then we get n times u out squared over 2 is negative delta p. Yes! Okay, so this is the expression we derived for u out, and note I've made one more simplification here by changing this delta p to a positive. It doesn't really matter if we make it negative or positive, it just kind of depends on how you set up your coordinate system. I mean, it is going to be a negative change because the pressure is less over here, but yeah. So how do we solve that? There's one more condition that we have to consider. P plus b squared over 2 mu naught equals constant, where b is the magnetic field strength. So where did this condition come from? Well, it's kind of complicated to derive. You can kind of think of it as like conservation of energy, or maybe Bernoulli's equation, if you're familiar with that. So this term here is called the magnetic pressure. And so what this is saying is that any change in pressure has to be exactly equal to the change in magnetic pressure. So if we say Fx equals 0, our magnetic field is going to vanish, so B equals 0. And then we have some B naught at L over 2. We can say that the change in pressure, so our dP, equals B naught squared over 2 mu naught. Okay, so then we plug that in over there. So we solve for U out, and we get U out equals B naught over rho m mu naught to the 1/2. Now, this might not seem like anything at first, but this is actually exactly equal to what we call the Alfvén velocity. Now, it's okay if you don't know what that is right now. Basically, the Alfvén velocity is the velocity at which electromagnetic waves move through the fluid. What's happening here is that the energy stored in the magnetic field is converted into thermal and kinetic energy within the plasma, a process that can be described by the diffusion equation. Using this equation, we can find an expression for the reconnection rate, which ends up being dependent on both the length of the diffusion region and the conductivity of the plasma itself. In the sun, for example, the estimated reconnection rate would be somewhere around 1/millionth of the Alfvén speed. Let's take a look at the actual value. What the Sweet-Parker model tells us is that a dissipation mechanism based on classical resistivity can produce the kinds of energy we would typically see in solar weather events. But in order to do so, magnetic reconnection would have to occur over a timescale that is much longer than what we actually observe. The problem here lies in the assumptions we've made about our system. See, the Sweet-Parker model assumes that most of the energy released during reconnection is due to classical resistivity, that is, collisions between particles. However, most of the plasmas we see in nature are collisionless, meaning these types of collisions are actually extremely rare. So this can't be the explanation behind reconnection in space plasmas. Instead, we have to look at the more complex interactions going on in our system. Okay, let's take another look at this generalized Ohm's law. So we've already deduced that this drag term can't be what's responsible here. We also know that the magnetic field ends up vanishing at the reconnection site, so it can't be this term either. And this is just du dt, this is just the change of momentum, so that doesn't really give us any information here. So what we're left with is the electric field, or the divergence of the pressure tensor. There are two possible explanations here. One is that the extremely thin and intense current sheet that develops during reconnection actually leads to fluctuations or turbulence in the electric field. These fluctuations scatter the electrons and produce what's called anomalous resistivity. Here's what this article in American Scientist has to say about it. Confirmation of the anomalous resistivity idea with numerical simulations had to wait nearly 20 years until computers were sufficiently powerful to explore reconnection and self-generated turbulence. The bottom line from this modeling effort is that anomalous resistivity develops, but only when the current layer and associated diffusion region are sufficiently narrow. Well, there are some really interesting results that have come out of this theory. What I really want to focus on is the second possibility, that the electric field is somehow related to the pressure divergence term. This would imply that the pressure is non-isotropic. In this model, electrons take energy from the magnetic field in the diffusion region as they are accelerated by the reconnection electric field. Because of their high thermal mobility, they are able to rapidly transit through and carry energy away from the diffusion region. The effect appears in the form of a pressure that is non-isotropic, or not the same in all directions. Therefore, it cannot be described by conventional fluid dynamics, although it has been well documented in computer simulations. Cannot be described by conventional fluid dynamics. You know what that means. It's time for quantum mechanics.
Oh my God!
Just kidding. It's actually a lot simpler than that. Remember what I said about our sun being made of both electrons and positive H+ ions? Well, as you probably already know, these particles have two very different masses, with the proton being nearly 2,000 times as massive as the electron. According to Newton's second law, that means they are going to respond very differently to the same amount of force. Now, this normally isn't an issue in plasma physics. We assume that any changes to our system happen slowly enough over a large enough region of space that the effects of inertia just kind of cancel out. But with magnetic reconnection, it's a totally different story. The Hall effect arises when moving charges are subject to a perpendicular magnetic field. Per the Lorentz force, positive charges are deflected in one direction and negative charges in the opposite direction. Eventually, this buildup of charge on either side creates an electric field. We're talking about a phenomenon which affects individual ions and electrons, which means we can't apply the principles of classical fluid dynamics here. Rather, we need an approach based on kinetic theory, which treats the system as an ensemble of different particles rather than one continuous mass. So how does the Hall effect appear in plasma? Well, let me explain. Okay guys, welcome back to Rowan's Derivation Corner. I'm wearing a different outfit. Let's get started. Okay, so just as a reminder, this is the situation we've got going on. We have some magnetic field lines that are closing in on each other that are about to reconnect, and this is the dissipation region. We all know Newton's second law, right? F equals ma. And as I mentioned, the mass of the positive ions in our plasma is much greater than the mass of the electrons. So if you imagine, we have an electron and some positive ion. If we have some force, pressure gradients or whatever that's acting on our plasma, if the electron goes, this far, the ion is much heavier, so it has kind of a hard time keeping up, so it'll only go, this far. So in our plasma, what that means is, say if, we have an electron here, we have our ion here, now there's going to be some kind of drift velocity of the ion relative to the electron, or of the electron relative to the ions. And so to make our lives easier, we're going to ignore all inertial effects on the electron. The electron will have some mass as well, and therefore some, inertia. But just to make our lives easier, we're going to imagine that the electron moves at the exact same speed as our reconnecting magnetic fields, or it has the same speed as, the rest of the plasma, whereas the ion, in a way, gets separated from the rest of the plasma. We call this being demagnetized. So we say that the ions are demagnetized. Okay, so previously we said that the magnetic force, or the Lorentz force, is QV cross B. And before we were assuming that this had no effect on our system at all. And so for simplicity's sake, we're still gonna assume that this Lorentz force has no effect on the electrons. But if we look at the ions, let's take this and zoom in. We have some ion with drift velocity going this way, and we have our magnetic field going this way. The force on this ion is going to be QVD cross B. So let's do our right-hand rule here. We have VD, put our finger this way, and then cross B. So the force should be going into the board. So this is the direction of our force. If you've ever seen this symbol, this just means into the board, so this way. Okay, so what does this have to do with the Hall effect? So we know that the ions are gonna be accelerated this way into the board. So let's take a look at this and flip it. So right now, let me add some axes here. We imagine that, call this X, Z, we're looking at the XZ plane. Let's look at what's going on in this slice. So if this is the XZ plane, we're rotating this way, and now we're looking at the XY plane. Ions are accelerated in this direction. And so you can imagine if we have a bunch of, ions and electrons, on average, they're going to be separated like this. So with all the negative charges at the bottom and the positive charges at the top. And so where the Hall effect comes in is that this charge separation is going to generate an electric field. So the result is that we're going to have an electric field going this way. And this is what's referred to as the Hall electric field. Let's put a little H subscript for Hall. So the electric force is Q times E, the electric field. And previously we said that this had no effect on our plasma because we had no external electric fields. But now, due to this charge separation, we have a non-zero electric field acting on our plasma. So if we look at the force on our electrons, our electric field is going this way and our charge is negative. So the force is going to be directed down. whereas with our ions, the charge is positive, so they're going to be accelerated upwards. So the result is that the Hall electric field slows down electrons and speeds up ions. Okay, I did my best to kind of draw like a flow chart here of what happens. So we start off with the electric force due to this Hall electric field, which is going to slow down electrons and speed up ions. So on the one hand, the electrons now have a drift velocity relative to the rest of the plasma. So now they have a drift velocity. Now they're going to experience the Lorentz force, due to this B field. So that's going to, change their trajectories and separate the charges even further, which overall changes the electric field and changes the bulk velocity of all of the electrons in the system. Okay, so that changes the electric field. Now that's going to change the electric force that both the ions and the electrons experience. It's also going to change the magnetic field because the magnetic field is, intricately related to the electric field through, Maxwell's equations. Okay, so that's going to change the magnetic force that all of these particles are experiencing. And on the other hand, the Hall field itself is slowing down electrons and speeding up ions, which in turn separates the charges further, which increases the electric field. So it increases the electric force. So what you have is this very complicated system where everything is, connected and everything sort of depends on each other. The nonlinear dynamics that arise as a result of the Hall effect produce a system of equations that are impossible to solve analytically. So, in order to make useful predictions about our system, physicists rely on computer simulations. Most papers use what's called a particle-in-cell, or PIC simulation. The basic idea here is that you give the computer a bunch of particles and some initial magnetic field, a set of boundary conditions, and a system of differential equations, and let loose. The computer will then use a numerical solver to continuously update your system over a very small time step. The result is that you get some really nice plots that look like this. And with the results of your simulation, you can calculate quantities like the reconnection rate, which ends up being somewhere around 0.1 times the alpha in velocity. There have been many, many, many studies which utilize this method, and they have all mostly produced the same results. The physical predictions that have come out of this model, from reconnection rates to electron distributions to the presence of a so-called Hall magnetic field which points out of the reconnection plane, have been measured extensively in both experimental and observational settings. Most of the data that has come out in recent years has been from NASA's Magnetospheric Multiscale Mission, or MMS for short. The mission seeks to study magnetic phenomena within the Earth's magnetosphere by using 4 identical spacecraft configured in a pyramid-like formation like this. In a paper by Torbert et al., the authors state, MMS observations of electron dynamics in the diffusion region match predictions made by one class of theories and models, nearly laminar ones that assume that the effects of turbulence and associated fluctuations on the electron dynamics are small. So that's it. Problem solved, right? Well, not exactly. The Hall effect model seems to give an extremely accurate description of reconnection in symmetric, two-dimensional systems where the magnetic field lines are facing anti-parallel to each other. That means in the opposite direction. When you start getting into different configurations, things get a bit more complicated. Remember the anomalous resistivity thing we talked about? Well, turns out it might be more consequential than we thought. As this review by Hesse and Kasich states, two-dimensional models demonstrate without exception that non-gyrotropic electron pressure tensor effects dominate at the location where reconnection occurs for symmetric configurations. Three-dimensional models of collisionless magnetic reconnection, however, can show significant contributions of the anomalous terms and the presence of substantial fluctuations at the reconnection site. In fact, the basic physics behind reconnection is still a hotly debated topic among scholars. Despite the massive amounts of MMS data that would seem to confirm the Hall effect model, scientists are not in unanimous agreement that this is the most accurate or complete model for reconnection. Here's a quote from one such scientist. While there is no first principles theory showing that the reconnection rate is 0.1, it was suggested that the dispersive behavior of the Hall term gives rise to faster flows at smaller scales. It should be pointed out that the Hall term is sufficient to give rates near 0.1, although it is of course not necessary since it was already known that the same rates arose in MHD with a localized resistivity. Some physicists, including the authors of my plasma physics textbook, actually favor a model that works within the resistive MHD framework that Sweet and Parker initially used to develop their theories. And don't worry, for all you quantum heads out there, I did search the web to see if there were any research linking magnetic reconnection in quantum electrodynamics, and I'm happy to report that I was able to find 2 whole papers on the subject. So, I guess plasma physicists just really don't like quantum mechanics.